In the previous video, we have seen that some observed behavior may appear irrational and inconsistent with random utility. It is only apparent, as these behaviors can be explained by more complex formulations of the concept of utility. In particular, this may involve subjective and latent concepts, such as perceptions and attitudes. In this video, we explain how latent concepts can be introduced in choice models. By definition, a latent concept cannot be observed. Therefore, if we need information about it, we will have to use indirect measurements. And usually, we are using so-called psychometrics. And I will describe what it is using an example from transportation mode, where we want to understand the perception people have about the mode. So the question that we ask respondents is the following. Please rate the following aspects of your commute by car. And then we list several aspects. And for each aspect, we ask the respondent to evaluate it on a scale that ranges from 1 to 5, when 1 is associated to very poor and 5 associated to very good. So the examples that we have here is that please evaluate the relaxation during the trip, evaluate the reliability of the arrival time, the flexibility of choosing the departure time, the ease of traveling with children and or heavy baggage, the safety during the trip, and an overall rating of the mode. As you can see, these concepts sometimes are somehow redundant or at least overlapping. In particular, when we ask overall rating of the mode, it overlaps with everything else. This is typical with psychometrics. As we are collecting indirect measurements, we are trying to collect as much information as we can. And also, the overlapping allows to get different facets of this information. Another example would be to collect indirect measurements about an attitude. And here, for example, we take attitudes towards the environment. For each question below, respond on a scale strongly agree, agree, neutral, disagree, strongly disagree, or no idea. And this should reflect your degree of agreement with the statement. The price of oil should be increased to reduce congestion and pollution. More public transportation is necessary, even if it means additional taxes. Ecology is a threat to minorities and small companies. People and employment are more important than the environment. I feel concerned by the global warming. Decisions must be taken to reduce the greenhouse gas emission. If you look at these statements, you notice that some of them would be more approved by people who are in favor of the environment, and some of them will be the opposite. So for example, suppose that I care a lot for the environment, I'm likely to support this first statement. I'm likely to support the second statement. I'm likely to disagree with this statement. I'm likely to disagree with this one. I'm likely to agree with this one. And I'm likely to agree with this one. So, as you can see in this example, when we design these questions, we try to minimize the impact of the framing problem that was discussed in the previous video. Okay, by mixing the way the statements are written, sometimes in one direction, sometimes in the other direction. So again, this is designed to decrease the impact of framing. So these psychometric indicators are obtained from questionnaires which are usually easy to respond, which allows the analyst to include several statements, many statements actually. The units are completely arbitrary, from 1 to 5, or sometimes from -2 to 2, or sometimes it's purely labeled, strongly agree, agree, and so on. And as we have seen in the previous example, we need to design it in such a way that we minimize framing. So in this context, in addition to the classical choice data, where for each individual we have the independent variables x and the choice I, now we have in addition a vector of psychometric indicators. So for each of these statements, we have the response that the individual has provided. And I denote it by capital I. Now, it's tempting to say, well, these indicators are more variables that we can actually use in our choice models. Well, it does not work in that way. Let's see why. So these indicators cannot be used as explanatory variables in the model, in the choice model. And there are two reasons for that. First, as we discussed before, the units are arbitrary, but so is the scale. So we decided to put 5 levels. It could be 10. So this is purely arbitrary. And this generates measurement errors. The interpretation of the scale may also vary across individuals. Some people have a tendency to overreact, especially for statements about topics that they care about. They may strongly agree or strongly disagree just to make a point. And then there is something called justification bias, which means that people will respond not because they believe in what they say, but because it justifies the decisions that they have made in the past. And this may produce exaggerated responses. So in general, these psychometric indicators are subject to a lot of measurement errors, and therefore we cannot include them as such in the choice models. And the second reason is that, well, if we have variables, which are these indicators, we cannot play with what-if scenario with this variable. We have no forecasting possibility. Indeed, I have no way to predict what these indicators will be in the future or for people who are not invited in the sample. So for these reasons, these psychometric indicators should be used in a different way. They cannot be used as variables in our choice models. A latent concept is something which is not directly observed. It comes from the Latin word hidden. So this concept is not new to us. In the standard models that we have derived from the beginning, there is a key latent concept that we have used throughout: utility. Utility is not a variable that we were able to collect. It's a variable that we had in the model. It was a function of observed variables, but the utility itself was not observed. So we know already a latent concept, and we will now go beyond that. In order to introduce the models in a simpler way, I will use some graphical conventions. I will represent latent variables using an oval-shaped box, and an observed variable using a rectangular box. And then I will consider two types of relationship between variables. On the one hand, I will have the structural relationship, which basically is based on my theoretical assumption about the phenomenon that I'm analyzing. And then the measurement relationship that relates the concepts in my model to the data that I'm able to collect. And finally, as we have seen already in many models, we will have error terms that will be involved. So the structural relations will be represented by plain arrows. The measurements relations will be represented by dashed arrows, and the error terms will be represented by dotted arrows. To familiarize ourselves with this convention, let's look at the classical random utility models that we have seen from the beginning. We have 3 ingredients. We have the utility, which is the latent variable, and we write the utility as a function of the explanatory variables that we observe, that we usually call the x, and an error term that captures things that we do not observe. And then there is the choice itself that we observe. It's a rectangular box. So in this context, we have a straight arrow here that represents the structural equation. So it's the relationship between the utility, which is latent, and the explanatory variable. We have Vin equals the sum over all variables of beta ik x I k n. So this is a typical structural equation in our framework. And now we have a measurement equation that actually relates the actual choice and the utility. A typical example is when we assume that the epsilons are I the extreme value, we obtain the logit model, and then the measurement equation says that the probability to observe a choice I is equal to e to the vin divided by the sum over j of e to the vjn. Okay, so this is an illustration of the graphical convention that I'm using in a context that we know well, which is the classical choice model. So now let's go back to our indicators. If you look at the literature on quantitative psychology, a typical analysis that they perform on these indicators is called factor analysis. Remember, our motivation to collect these indicators is that they would reveal something about the latent variables. And a factor analysis is basically designed to represent this model. So we have our latent variables here, which are represented by an oval shape, and these indicators are measurements of these latent variables. But of course, these measurements are subject to errors, as we discussed before, so I denote these errors by psi I n here. I will show you an example of factor analysis when I will come to the case study. But basically, that's the representation using our drawing convention. Now we extend the factor analysis approach by including a structural equation. So somehow we would like to explain the latent concepts using concrete explanatory variables. So we would like to explain my attitude toward something or my perception of something as a function of my age, my income, my level of education, and so on. This is the idea. This structural equation is represented by this arrow here that relates the observed explanatory variables to the latent concept here. And here we have an error term. So you see the setup is quite similar to the one that we had for the choice models. Okay, there was a similar representation. We start from observed variables. From a structural equation, we obtain a latent concept. And then we have a measurement equation that allows us indirect observation of these latent concepts. There is a minor difference that is represented here by this error term, which captures all the measurement errors that are associated with the indicators that we commented earlier. Now the idea is put the two things together. We had the choice model based on the utility concept, which is a latent concept. And now we have these additional latent variables, attitudes, perceptions, what have you, which are also associated with an observation, the indicators, and explained by the explanatory variables. On this picture, you see the two pictures that you have seen before. On the left, we have the choice model that we have introduced first. And on the right, we have these latent variable model that we have included as an extension of the factor analysis. And now when I put them together, the idea is that I will explain the utility as a function of the latent variables. So it means that the utility that are associated with a good or an option will depend on my perception and on my attitudes. So if I perceive McFadden to be a very good winemaker because I've been influenced by an additional alternative, well, my utility for these alternatives will increase. This is the framework. Okay, we put the two concepts together and we use the latent variables to explain the utility function. So this is sometimes called an hybrid choice model. So it's a choice model with latent variables. And this is summarized with this picture. In this video, we have introduced a framework to include latent variables into choice models. In the next video, we define step by step the likelihood function associated with this framework.